techniques, particularly the K-map, which happens to be a well-structured technique for minimizing logical expressions for implementation. We have also discussed about the significance of minimization, prior to the implementation of the logical expression. So the only challenge with the K-map is that although it is very, very powerful and useful, it is a 2D representation, as we have seen in the past. So if you have more than 4 variables, right, because in 2D you can always represent 2 variables on one side and 2 variables on the other side. That's if you have up to 4 variables. But when you have more than 4, then it becomes very complicated. And that is where the QM technique, otherwise known as the tabular method, comes in. So with this particular technique, it is more robust and allows you to deal with expressions with variables that are more than 4, right? Yeah, so this method works first of all by identifying what we call the prime implicants and essential prime implicants. These are the foundation for the QM technique. So because of that, we would like to look at what these prime implicant and essential prime implicants are before we dive into the actual QM method. So we can all recall that in our K-map, we have some entries into the K-map. And these entries are ones. We represent them by ones. These ones are the ones that are in the output function in our K-map, in our truth table. Since we represent these entries into our K-map by ones, so each of these ones or a group of these ones is considered to be an implicant. So in other words, an implicant is any entry in the K-map. So a group of ones or single one which are adjacent and can be grouped in the K-map, they are called implicants. So all the possible group of ones that we can find in the K-map, they are all referred to as implicants, right? And then we have prime implicants. So when we talk about prime implicants, we are looking at the largest possible group of ones that we can have. Don't forget that in our K-map, we are always grouping ones. And based on the rules of the grouping, we are supposed to group as many ones as possible, right? So this is important. So if you take a look at this table here, we have 4 ones in the table. In other words, we have 4 implicants. But out of these 4 implicants, there are possible ways we can group them. So first of all, we have to bear in mind that we need to form as large group as possible. So what is the largest possible group that we can form in this table? What is the largest possible group that we can form in this table?
2.
In this K-map. What is the largest
3.
possible
7.
group?
3.
4, sir. 4.
3, sir.
2.
What is the largest possible group that we can form? in this table?
Say 3.
It's
Three,
better
sir.
to understand the question, because understanding the question is very important. So you need to
We
understand the
can't form
question
groups
first.
of 3. It's true.
If you don't understand the question, you always provide wrong answers. So let's understand the question. What is the largest possible group?
2.
Of ones. It's 2.
2.
2
The
group of
largest
ones.
possible group is a group of 2 ones. Right? That's the largest possible group. So if there were more than 2, if there were a group that has more than 2 ones, then that would be the largest. So don't forget that each group is in the powers of 2, right? So you can have a group of 2 ones, you can have a group of 4 ones, you can have a group of 8 ones. Please, let's make sure that we are muted, okay? Bismarck, who is Bismarck? Can you mute yourself? Please always remember that you are in class, so we don't need external disturbance. All right, so now we are dealing with informing the prime implicants. We aim to have the largest possible groups that we can form. So here, since the largest possible group is 2, so we form 2 group here. So we have 1, we have the top one, and we also have the middle one here. These are all possible group of ones, right? But you notice that even though we have 3 set of groups, and since we have 3 set of groups, it means that each of them represents a prime implicant. Each of them represents a possible group of ones. So we have 3 different sets. So we have 1, we have 2, and we have 3. But as far as the essential prime implicants are concerned, if you look at all these prime implicants, you realize that we have one group that has completely been consumed by other groups, even though it is also a group, but that group has been consumed. Which of the groups has also been covered by other groups?
Group 2, sir.
Group 2, very good. So you realize that whilst group 2 is counted as a prime implicant, in reality, group 2 has already been covered by group 1 and group 3, making group 2 redundant. So once group 2 has become redundant, it means that anytime you are forming your final expression, group 2 won't play any significant role. So we can ignore group 2 and only focus on group 1 and group 3. And they become what we call the essential prime implicants. So essential prime implicant is a prime implicant in which at least it has one member which is not covered by any other group. And the reason why group 1 and group 3 are essential because you realize that each of group 1 and 3 has one of their members being covered by group 2. But it still has one member that has not been covered, which makes it essential. So in other words, if all your members are completely consumed by other groups, then you fail to become essential. But if you have at least one of your members which is not covered, then that qualifies you to become what? Essential. So looking at this table, what are the essential prime implicants? let's try and identify the essential prime implicants. We can use the colors, maybe. And why do we think they are essential?
So please, the one in blue up there.
Which one?
The one at the topmost corner. The one up there.
This one.
Yes, please.
That
Because
one is.
yes, please. None of them is covered by another group.
Okay. All right. So let's hear from other people too. So she said that Benedicta said is this one, right? This top ones. Okay. Emmanuel, let's hear from you.
Yeah, please. The one in the red or pink color is also an essential primary cut because it's just the down part of it that has been covered and the top part is not consumed by the other group.
Very good. So maybe this color is orange. So the orange guy here is essential because we can see that it has 2 ones that have not been covered by any group. Good. Enoch, let's hear you.
Okay, please, the one in blue, the ones that are overlapping. I'm just hammering on what Benedicta or my colleague said. It's overlapping with the other ones that are at the bottom. The blue, yes. So the other ones that are at the bottom are covered already, but the ones on top are not. So it's essential.
Perfect. This is an addition to what Benedicta said earlier. So Benedicta's presentation was not complete. I was expecting her to just hit it as Enoch did. So Benedicta only focused on the top ones, but you realize that this group is not complete because this is just a half of it. And that is why we are not completing it this way. The other half is at the bottom here. So you realize that we are not using the full square to cover this because it is joining with the guy below here to form the full square. So if we are considering it, we have to considering all the 4. 1, 2, so 0, 1, and then 8, 9. They form the group of 4 ones. And you can see that whilst the bottom one, 8 and 9, is already covered by the yellow, the top one, 0 and 1, is not covered. So it means that this 0, 1, and 8, 9 form essential prime implicants, right? So far we have 2 that are fully qualified. So let's look at the remaining. So Vida, your hand is up. Let's hear from you.
Please, so the green one. But they are non-essential because they are all covered. The ones are all covered.
Okay. So are you saying that that blue one in the middle is non-essential?
Yes, sir. So the blue one in the middle, that one is non-essential. Yes, because it's all the ones are covered.
Okay. All the ones are covered.
Yes, please.
Okay. Good. Any other? Okay, Emmanuel, let's hear from you.
So also the yellow ones in box number 12, 13, 8, 9 are also non-essential because all the ones have been consumed by other groups.
Very good. So you can see that the ones we are actually labeling as non-essential are actually in one way or the other being consumed by other groups. But of course, if you take a critical look at those two, those non-essential,
Personally.
we need to pick one of them. We cannot pick both, because when you are forming your final expression, the principle is that your essential prime implicants are all members of your final expression. So if we were to write our final expression from this schema, we will consider the orange one would be parts. This blue guy here would also be parts. And now, you also notice that when you take the orange guy and this blue guy, it doesn't cover the whole ones in the table or in the map, because 12 and 13 is still there, which is not covered, right? So the only way we can cover 12 and 13 is in two ways. It's either we use the blue here or we use the yellow here. These are the two options. So in our final expression, since we have two essential prime implicants, and both of those two, right, both are trying to cover the same group of ones. So in our final expression, after selecting the essential ones, we have to choose between these two non-essential ones. We have to pick one, because we cannot use both, right? So we can decide to use the yellow one. If you use the yellow one, it means that this blue one becomes redundant, right? If you also choose the blue one, then the yellow one becomes redundant. I hope this is clear. Yeah, so let's take note of this going forward. So once we can understand these essential prime implicants, we are good to go, right? So let's quickly move on to look at the Quine-McCluskey technique, which is also known as the tabular method. Okay. So as I stated earlier on, it simplifies Boolean expressions into the most simplified form, just as we're doing with the K-map and the algebraic manipulation. But it uses what we call the prime implicants. And once we have some fundamental understanding of what prime implicants are, it becomes much easier. And this is very, very useful, particularly when we are dealing with expressions that have more than 4 variables, like I stated earlier on. But this technique follows, some algorithm or some procedure, which we just follow and then we apply. So there are about 8 steps that we need to follow, to accomplish any minimization problem with the QM method. So the first step is, when you are given an expression, most times we are given these expressions in a form of mean terms, right? So we have to first construct our table, our truth table, with these mean terms. And then we group these mean terms according to the number of ones. So we are going to write each of the mean term in its binary form. So for instance, this is an expression given us, and these are the mean terms in the expression. So we write each of these mean term in its binary form, right? when we write each of the mean terms in its binary form, it's definitely going to contain some zeros and ones. So now we are going to group these mean terms based on the number of ones that they have. So mean terms that have the same number of ones will go to one group. That's the way we do it. So we start from 0. Mean terms that have 0 ones, we group them. Mean terms that have single ones, we group them together. Mean terms that have 2 ones, we group them 3 ones in that order. So we are going to have a group that consists of only mean term with the same number of ones. That is the first step. So this guy says group the mean terms according to the number of ones present in their binary representation in ascending order. So you can see that. So we are going to group them, these ones, in ascending order, right? So let's look at that. We have been given this expression, simplify the function below using the tabular method. So this is the mean terms that we have been given. So the step 1 says, first of all, we need to write these mean terms in their binary form representation. So we have a truth table. So we have 0. We write it in the binary representation. And don't forget that these are the variables, the input variables, X, Y, and Z, right? So since there are 4 inputs, it means that each mean term would have 4 bits to represent it, 1 for each of the variables. So we have the first term is 0, 0. So we have our inputs here, X, Y, and Z. And of course, we can represent the mean term symbol, this M0. The second one is 1. So we have to write 1 in binary. And since there are 4 variables, it means we need 4 bits. So 0, 0, 0, 1. We have 3. 3 in binary is 0, 0, 1, 1. We have 7. 7 in binary is 0, 1, 1, 1, 1. We have 8. We have it. We have 9. And we have 11 and 15. So you see that with this first table, all we are doing is to write the given mean terms in their binary representation. And then we represent them using their mean terms form, like the M0, M1, all the way to whatever we have. So this is something that we can all do, right? Is there any question on this? Are we all clear on this?
Yes, sir.
So,
Take that part again, please. Please take this part again for me, please.
so we are going to write all our mean terms in their binary representations, right? We are going to write our mean terms in their binary representation for 1. So it just means that we are writing all these things in binary. That's all. Right. So once you write them in binary, that is the first step. And then each of them, we use their mean term symbol to represent it. Right. So we have this. So once we are able to get this, the next step is we do the grouping. So here it says that group the given mean terms according to the number of ones present in their binary representation in ascending. So we are going to group the ones. Now, you realize that if you check each of these binary representation, each of them may have some ones, some number of ones. Now, considering M0, M1, M3, all the way to our M15. We are going to group them. We group them based on the number of ones that each of them has. Right. Vida, do you have a question?
Yes, sir.
Okay, go ahead.
Sir, please, so this table is not like the truth table, right?
Well, it's a table. You can call it truth table or however it is, but it's just a table that represents your numbers. So you can call it a truth table.
Sir, but the truth table that the came up truth table is different from this table. So you see the X part 0000, like the 81000111, and the
Which one?
Y part, say for the K map.
Please, this one is not came up.
Yes,
Okay.
sir. So, but the reason why I'm asking, I'm saying that this one is different from the K map.
Yes, this one is not came up. This one is
Alright.
a table for the mean terms that we are given. We are writing, obtain the binary representation of the mean terms. So we are just writing our binary, our numbers in their binary form. That's all we are doing here.
Oh, okay, sir. Yeah, I understand now.
Okay. So once we do that, then we can move on to look at our first step, which says that arrange the given mean terms according to the number of ones present in their binary representation. So now we are going to group them. So we start from group 0, group 1, group 2, group 3 in that order. So when we pick a group 0, it means that we check all these mean terms. Those that have 0 ones, they belong to group 0. So which of these mean terms has 0 ones?
M0.
M0, very good. So you see that M0 has 0 1. So when we come here, under the group 0, we put M0 there. And then we write out the representation, the binary representation. That's all. Then we come to group 1. How many of the mean terms have only a single one?
M1.
How many of the mean
M1,
terms?
And
2, M1 and M8.
M1, M8.
M1 has single one and M8. Very good. So it means that M1 and M8 also has single ones, right? Very good. Then we move on to 2.
M3,
We move on
M9.
to 2.
M3
So let's check.
M9.
We have
M3
M3.
and M9.
Yes, so
M3 and
M3
M9.
and M9, right? So they are also here. Then we move on to 3. 3.
M7,
M11.
M7,
M11, M7 and
M11.
M11. M7 and M11.
Okay. So we have M7, we have M11. Very good. So we have M7 and M11. And then for 4 ones,
M15.
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 Yeah. So M15. Very good. So it means that we have all these grouping down. So now we are done with step 1, right? So let's look at step 2. Step 2 says, take the mean terms from continuous group if there is only one bit change to make a match pair. Place the dash symbol where there is a bit change accordingly and keep the remaining bit the same. Okay, so we are going to do step 2 and step 3, right? We are going to do step 2 and step 3. So step 2 says that take the mean terms from continuous group if there is only a 1 bit change to make a match pair. So what does this mean? So we are going to compare each group with the preceding group. Sorry, with the following group. So we take group 0 and we compare group 0 with group 1. Okay. So if you take all the mean terms of group 0, you compare it with all the mean terms of group 1. So when we compare, what we are actually going to do, we want to see if each element of group 0 matches with an element of group 1. And what do you mean by matching? So for group 0 and group 1 to match, it means that when you compare their binary values, they should differ in only 1 bit position. When you compare their binary values, they should differ in only 1 bit position. That means that those two mean terms, they have a match pair or they form a match pair. That's the meaning. So we are going to do the match pairs. Now, when you are doing the match pair, we take each member of one group and compare with all other members. So when you take this group, you take M0, you compare with M1, take M0, compare with M8, then we are done. So we compare this with all the groups here, all the mean terms here. So for each of them, we check if you compare M0 and M1, is there a match between them? There is a match only if they differ in only 1 bit position. So let's compare M0 and M1. Do you think there is a match between them?
Yes, sir.
Yes, sir.
Yes, please.
Yes, sir.
Yeah, I think the last bit.
Yes, sir.
Yes, sir.
Good. So where is the match?
At the last
The last
end.
bit.
Last bit position.
W.
Yes, at the last W, at the last
Very,
W.
very good. So since your M0 and M1 match, it is that we are going to have a match between M0 and M1. So we say that M0 and M1, they have a match pair. This is the way we write it. So M0 and M1 have a match. And if they have a match, we will put dash at where they differ. That's what this was saying. This was saying that place a dash symbol where there is a bit change accordingly and keep the remaining bit the same. So it means that where we realized, okay, we put where there is a bit change, we put a dash there. Is that okay? We put a dash here. Okay, good. So the remaining bits that are common among the two, we keep them the same. We only put dash at where the 2 bits differ. So we compare M0 and M8 also. Is there a match?
Yes, sir. X.
Okay.
Yes. So where do they have a bit change?
The first
X.
bit.
Bit
The first
position.
bit.
First bit
Very
position.
good. First bit. So it means that here we will also have the match at the first bit position, right? Good. So we are done with group 0. So we are comparing group 0 and group 1, and we are done with that. So we call that group 0. So now This is done. Now we compare group 1 with group 2. This is the way we'll be doing it. So group 0 with group 1, or group 1 with group 2, and group 2 with group 3, group 3 with group 4. Right. Good. So that is okay. So now let's take a look at group 1 and group 2. So in this case, we are going to compare M1 with M3, M1 with M9. Then we take M8 with M3, M8 also with M9. So we are going to have 4 comparisons. So let's look at them. M1 with M3. Is there a match?
Yes, please.
No,
Yes.
sir.
At the Z.
No, sir.
Yes, yes.
Yes, please.
Very
It's a
good.
Yes,
At
match.
there's
the
a match.
Z.
The
At the
second
Z.
one.
Good.
At the Z.
Good. So M1 and M8, is there a match?
Yeah.
Yes.
Yes, please.
Sir, come
M1
again.
with M8.
M9.
Sorry, M1 with M9. M1 with M9. Sorry.
Yes,
Yes.
please.
There's a
Yes,
match.
please. There's a mark. The W.
So where do they differ?
They are the X.
The
The
W.
X.
X.
At X. Very good. So it means that M1, M3, M1, M9, there is a match, right?
Yes, please.
Yes, sir.
Good. So let's see. So M1 with M3, there is a match, and they differ at Z. M1 and M9 also, there's a match. They differ at X. All right. Good. Now, let's look at M8 with M3, M8 with M9.
No, sir. There's
No,
no
sir.
match.
There's no match.
There's no match.
There's no match.
Yes.
Yes,
sir.
please.
Okay. Then let's look at M8 and M9.
There's a match.
Yes,
There
please.
is a
There's
match.
a
At the
there's a
At
W.
the
match.
At the
W.
W.
Very good. So it means that, and where do they differ?
At the
At
W.
W's.
W.
The
At W. Very good. So we have this also, they differ at W. So we put the dash at W. So we are done with this group also. So now we take group 2 and compare with all the members of group 3. So it means similarly, M3, M7, M3, M11, then M9, M7, M9, M11. Right. So let's do the matching.
There's a match.
So M3, which one does M3 matches with?
M,
M3
The
matches
Y.
M3.
M7.
The
At the
Y.
The
Y.
Y. The
At the
difference
Y.
is the
Yes.
Y.
M7 at the Y.
So the Y.
Okay, so
The Y.
M3 matches with M7, right?
Yes,
And they
please.
differ
Yes,
at
sir.
Y.
Yes, please.
They differ at Y. Okay, good. What about M11? M3 and
Yeah,
M11.
Yes, sir.
there's a match. There's a match
match.
also.
Yes,
Mhm.
there's a
And they
match.
differ at where?
At Z.
X.
At Z.
At X
At
or Z?
X.
Say
Z.
M3 and 11.
X. At X. At X.
Say BC.
It says
X.
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 It's
X.
X. Very
X.
good. So it means that M3 goes with M7 and M3 matches with M11. Very good. Then let's look at the M9. with M7, M9 with M11.
They differ at Y. M3 and M7 differ at Y.
Mm-hmm.
They differ at Y and has a match on the rest.
Okay, so they differ at Y, right? Good. So I hope I'm seeing a hand up here.
We are doing
Patrick Edu,
M7.
you have a question?
Alright. Yes, sir. I have a question.
Okay, can you go ahead?
All right. So my question is, we just spoke about M8 and M3, and everyone was saying there's no match, but I could see a match over there.
Which one?
The very first one is the very first one. When we compare M8 and then M3 at the S column, they are different. The S column has M8 1 and then M3 0. Is that not a match? Then the third one is the
No.
Z
Can
column.
you
They
take
also
that
differ
again?
at Z.
Please, can you take that again? M8 and what?
M8 and M3. So
Okay.
at the S column, M8 has 1 and then M3 has 0,
Yes.
which are different.
Yes.
So is that not a match?
No, but you can see that the Z column too, there is difference. Can't you see that?
Yes,
sir.
I also saw that. That's why I'm a bit confused.
The match only happens if there is only changes in one bit position, not more than one. So if you have more than one bit
Okay.
position, that means there is no match.
Oh, okay, sir. Thank you.
Yes, that is why here we did not include M8 and M3. If you look at this, we don't have M8 and M3 because there is no match. Is that okay?
Yes, sir.
Okay, good. So let's move on. Let's look at the last one, M9 and M7, M9 and M11. Where do we have the match?
No match between M9 and
No match
M7.
between
But
them.
there
No
is a
match.
match with M9 and M11.
No match
No
between,
match.
okay,
Between
and then
M9
M9,
and
M11.
M11 differ at Z. At Z.
Yes.
No match between M9 and M7. But a
No
match
match.
between M9 and M11.
Yeah, so M9 and M11. Good.
Yeah.
So M9 and M11 is good, right? Good. So the last one is M3 and M4. So we compare M7 with M15 and then M11 with M15. And that will be the last comparison. So let's look at that. What do we have?
That is the match.
There's a match.
So there's a
M11
match.
and
Match.
M15
There's a
has
match in the first X.
There's a match.
7 and 15
There's a match.
A match.
There's a
Yes.
match
Yes.
and
There's a
11 and
match.
15 also there's a match.
Yes. Why?
Yes,
Very
Yes.
good.
there's a
Yes.
match.
So
That's why.
in both cases there is a match. You can see this, right? Good.
Yes, sir.
So this is an iterative process. And as computer science and IT students, when we say something is iterative, I'm sure we all understand, right? So it means
No.
Yes, sir.
Yes, sir. Yes, sir.
No, sir.
okay, when we say
I
something
don't
is
understand.
when we say something is iterative in computing, we simply means that it is repetitive. Something that repeats itself a number of times. Is that okay? Okay.
Yes,
Yes,
sir.
sir.
So if I tell you to run from one end of your room to the other end of your room 10 times, that's iteration. So you are doing it a multiple time. The same thing. You do it a number of times. So in programming, we always talk about iterations or looping. When you put something in a loop and it has to run a number of times. I think this is a programming concept, right? So we are going to do this iteratively, which means that we will repeat the whole process again until we get to a point where we can't continue with the process. So what does this mean? So we replicate the same approach. Now we take 0, compare with 1, take 1, compare with 2, take 2, compare with 3, just as we did. But this time around, remember that you are comparing this with this, this with this, this with that. Okay? Then you take this one also with this with this, and then this also with this. Are we good? Very good. So we are going to have how many comparisons?
Sir,
Six.
please, I'm
It's
a
six
bit
comparisons.
confused.
Six.
Very good. So we are going to have 6 comparisons. And we compare everything, including the dashes. So you compare if they also have the dash in the same position, it also counts, not only the ones and the zeros. So we compare M1 and we compare this, we call it M0, M1 with M1, M3. So let's look at it. Is there a match?
No.
Okay. So the first and the first, there's no match. Okay, so M0, M1, M1, M9. Is there a match?
Yes.
No,
No.
no,
They differ
no.
No,
There
in
is a
they
match.
differ in
X.
There's no match.
X and W.
there's
they,
They
no
they
differ
match.
in
differ
X
in
and W.
X and W. Very good. So there's no match.
X and
So
W.
M0, M1, M8, M9.
There is a match.
There's a match.
There's a match.
Yes, sir.
Yeah,
So
there's
where do
match.
they differ?
They differ at
They
X.
differ at
X.
X.
Very
X,
good. So
X.
it means that we are going to put X there. So now we are going to have 2 dashes. They already have dash and dash here, and dash here, right? So this is what we are going to get. So you see here, M0, M1 matches with M8, M9, and they differ in this position. This is still intact. We don't touch this. They differ here. So now we have 2 dashes, right? Then we move on to the last one, 0, 1, 8, 9.
I think
That's
that's
0,
what we
1,
just did.
8, 9.
So that's what we just did.
Oh, okay. That's what we did. So now 0, 8, 1, 3.
There is not a match.
There's no match.
There's
There's
no
no
match.
match.
0, 8, 1, 9.
No match.
There is
No
no
There's no
match.
match.
No match.
0, 3, 0, 8, 8, 9.
Sir,
No
there's
There's
no
a
match.
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 No
Sir.
match.
And they differ
There's
No
a
at
match
match.
at X.
There's
At
no
W.
match.
X.
So there's no
Are you
match.
sure? Are you sure?
there's no match.
No.
Yes.
Yes.
They differ
There's
at
no match.
X and
Match
W.
At X
And
and
W.
W. Okay.
X and W, there's no match.
Okay. Then which one again?
That's all.
I think that's all for group 0 and 1.
Okay. Okay. But okay, let's check again. With 1 9. Check with 1 9 again.
So please 1 9 and what?
08 and 1 9. 08 and 1 9.
There's no match.
So there's no match.
There's no match. Oh.
No match. They are the same. They are the same. There's no match. They are the same throughout.
If they are the same, then there's a match.
Yes. Okay.
There is no match.
There's no match.
There is match.
I
There
think
is a match.
they match when they have it. They have one,
Sir, please, I'm confused. Oh.
Don't be
Don't
confused.
be confused.
I'm
It's
confused.
it's a process, so we are going through. So we are comparing. Yes, it's a process we are going through. So let's all go through it. So what do we have? This and this.
X, they both have dash.
Yes.
At Y, they both have 0. At Z2, they both have 0. And at W2, they both have 0.
Okay, wait. Let's go back here and see again. The M0, M8, what do we have? Dash,
M0.
right?
Yes, sir, we have dash there.
M0, M8, we have the dash at X. Is that not it?
X and dash at W. Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Very good. So M0, M1, where do we have the dash?
We have the dash
W.
at W.
That's W.
At W. Okay.
Yeah.
Now let's move on to, so it means that this is correct. For M0, M1. I just want us to recap again. M0 and M1.
So there was a
M0, M0, M1. The dash is at W, right?
Yes, sir.
Yes, sir.
Okay.
W.
M0, M8.
The dash is
M0.
at S.
It's at X.
It's at X.
It's at X.
Is that what? X. Okay.
X.
X.
Yes.
Yes.
So it's at X. So let's see. M0, M8 is at X. Very good. Now, let's look at M1, M3. M1, M3.
At Z.
It's at
And
Z.
Z.
Sir,
And
at
Z.
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 Okay. So M1, M3.
Yes, sir.
Yes, sir.
Okay, so M1, M3 differ at Z. So we have this. So let's see that M1, M3 they differ at Z. So you have 0, 0. Good. So M1, M9. Let's see M1 and M9.
They differ at X.
They differ at X.
They differ at X. M1,
please.
M9 they differ at X. So
Yes.
you have 0, 0, 1. M1, M9. M1, M9 they differ at X, right?
Yes, sir.
And you have what?
M8, M9.
No. M1 and M9. And so they differ here. They differ here, right?
Yes, please.
Yes, sir.
Then the rest are what?
The same.
0, 0, 1. Is that not it?
Yes, please.
0, 0, 1. So let's check for M1, M9 here. But you see that for M1, M9 here, we have kept 0, 0, 0 here. Can you see that?
Yes, please.
Yes, sir.
Yes, sir.
So this is supposed to be what? This is supposed to be 1, not
One.
0.
Mhm.
Nobody saw that. Okay. So it means that over here, we were actually comparing M0, 08, and is it 08? 08 and
08 and 19.
19. Very good. 08 and 19. What do we have?
Yeah, they will match.
0, 8. They
The
don't match.
Because
difference is at
initially we're
At
saying
W.
that they are all the same. Is that not it?
Yes,
Yes,
sir.
Yes.
please.
Yes. So, and the problem is that because we missed this guy, that's why we're saying that they were all the same. So there's no match. But
Yeah, very
since
good.
this is 1, it means there's a match and they differ at where?
W.
W.
At
Very
W.
good. So it means that here we have 08 and 09, they match and they differ at W. Is this okay?
Yes,
Yes,
sir.
please.
Good. So we move on. So now we compare this guy. We compare this
Hello.
guy. And we compare this guy. So 1337. 1337.
And this
No match.
There's no
No
match.
match.
No
There's
match?
no match.
Okay. 13311.
No, there's a match.
13311.
There's a
No
match.
no
match.
They
match.
differ at Z.
No match.
No
They
match
differ
here.
No match.
said no match.
They differ at X and Z.
Some people are seeing what some of us are not
No
seeing.
match.
They
No
differ at
match.
X
Yeah,
and
no
Z.
match.
There's
So
no match.
no match. No match.
It's more than one, so there's no match.
Hey.
Okay, so 13911.
There is a match.
There's a
There's
Z.
a match.
It's
There.
They
X.
differ at
X.
X.
They differ at
X.
X.
Different
Very
X.
good. So
Then yes, there's a
X.
match.
13911. So 13911, there is a match and they differ
There's
at
a
X.
match.
Good.
oh fuck.
So
Yeah.
now let's look at M1. Okay, 1937.
1937.
No.
No match.
No match.
No
No match.
match. No match.
No match.
I know for some people the whole course should have been like this.
No match.
Finding matches and not matches. The course should have been about.
Okay, I think there's a match.
Yes, sir.
Hey.
But there's no match.
There's
So,
no match. First, no
1937.
Should have been great.
1937, no match.
Yes, please.
Okay,
Yes, sir, no match.
19311.
match in Z.
There's a match.
At Z.
19311.
There's a match.
There's a
At
match.
Z.
Then
At
They
there's
Z.
differ
match.
at Z.
As in,
At
Z.
what?
Zebra.
Z. Okay.
Yes, I
So this, we are comparing this
and that.
with this. So the difference is here at Z. Good. So 19311. 19311, there is a match and it's
At
at Z. Good. So let's continue. 19911, is there a match?
No match.
No match.
Okay. M8 31137. This.
No match. No match.
Okay. 89311.
So wait, like I'm confused at M8 311. M8.
Please take it
We are
again. Which one are we
comparing
on?
this. We are comparing this and this.
Let
We
me
are
see
comparing
the
them so you can easily see. They differ
No
here.
match.
They differ
No
here.
match.
They differ here.
match.
They differ everywhere. So there's no match.
Two out.
everywhere.
So let's move on to this with that. This with that. Let's see.
No match there.
No
No
match.
match.
Now
Very
no
good.
match.
No match. So this with that.
No match.
No match.
Yeah,
They
No
differ
match.
here and they differ there. Okay,
No
good.
match.
So it
Away
means that
matches. No match.
we are done with this. So we move on to 2 and 3. 2 and 3. So 2 and 3, 311, sorry, 37, 715.
No
So
match
please,
there.
can you use
No
a
match.
different color? It's plenty on our eyes. So
Yeah, you are right.
Some of us we have eye problem.
Let me use
I will
let me use
continue to you are confused.
let me use a
It's
blue
plenty.
color. So this and this now. This and this. Sorry. This.
No
and
match
this.
there.
Let me take this again. Some people have color issues, so they are not
Say
able to
use
keep
green.
track.
Say use green.
What?
Some of us we have eye
Green.
problem.
The
blue is
green.
similar to what we are seeing. If you can use a different color.
Okay,
use
okay.
Yeah,
yellow.
sir.
Okay, so let me
Green.
use the green. So this and this. The green is okay, right?
Yes,
Yes,
please.
sir.
Yes, yes.
This and this. Okay, so let's look at it. So 3, 7,
There's
No
7,
match.
15.
no match.
No match there.
No match.
They are not matching.
We are done with all this, so let me remove them. Good. So 7, 3, 7, there's no match. Okay, now 3, 7, 11, 15.
There is
No
a
match
match.
there. No
They
match.
differ
There's
at
a
X.
There's a
So
match
there's
So
a
there.
there's a
match
match.
There's a match, and where do they
Yes.
match?
at X.
There's a match
X.
there.
X.
At X. Leave
X.
at X.
At X. Very good. So 3,
Yes,
7, 11, 15. So 3, 7, 11,
3, 7,
15.
11, 15.
And they
There's a
match
match.
at X. Good.
Yes.
So
X.
now we move on to look at this, and that. So 3, 11, 7, 15.
They match.
This
There's a match
is,
there.
Why?
it
They
is.
match.
There's a match. Why?
There's a match at where?
There's a
Yeah,
match
Why?
at
why?
Y.
Say at
The
Very
difference
Y.
in why?
So, and 3, 11, 11, 15.
3,
With
11.
this,
No match.
Say
No match there.
No
No
match.
no
match.
match. No match.
very good.
Yeah,
So the
there's no match.
last one, 9, 11, 7, 15.
No match.
No match.
No match there. No match.
So this guy and this guy, no match.
Yes, please.
This guy and this
No
Sir,
guy,
match
please,
there.
can we check
No.
the 3,
No
11,
match.
and
No
11,
match.
15
There are
again?
no match.
there's no match. Okay.
Yes,
Yeah,
So you
please.
the
have
two of
only
them no match.
Say,
you have
please,
only
someone
2
say
So,
matches.
check the
let's take
311.
the 9, 11, 7, 15 again.
Hello.
Which one?
The 3, 11, and then the 11, 15. Sir, please, let's take it again. There's a match.
We
We
have
said
already
it.
gotten 2
Already.
matches. We have 2 matches already.
So let's go over
Yeah.
it again. It's
Which
like
one? Which
there are
one?
matches there.
Which
So
one?
he said 311. 311. 9.
311
Yeah,
and
there's a
what?
match.
311 and what?
And then 11, 15.
There's no match.
7:15.
There are two
This-
differences.
This
There are
and
two
Yeah.
this.
different.
They differ
There are
here.
two different.
They differ
This is
here.
all.
So
Yes,
there's no much.
there's so much.
It looks
Yes.
like some people have not taken breakfast yet, so they are seeing things too.
Because some of us are.
Yeah,
Go
I
for
can
it.
understand. Because this thing, you have to be very, very, very critical. Otherwise, you make a mistake.
Yeah.
Yeah, so I
Yeah.
understand.
And the steps
All
are
right,
plenty.
exactly. So, as a computer science student, or what would you suggest? What's the best way to get this done instead of this manual process?
Yep.
So now, let's look at this. This is a new table we have. So we continue to check if we can still have a match. So 0 and 1. 0 and 1.
Yeah, no match.
Yeah. So you
Yeah,
see
please
that this,
be putting the thought so that we'll be seeing it.
so this and this,
No
Yeah,
much.
there's no match. No
No
match.
match.
No match.
very good. And it's the same thing, this and this.
No match.
Because
No.
if you
No
check,
match.
you realize that both match pairs are the same now for each group. So if one doesn't match, it means the other one will not match. Can you see that?
Oh,
Yes,
okay.
please.
Yes, because this and
Yes,
this
yes,
are now
yes.
the same. So if this
Okay.
one doesn't match with any
Uh-uh.
of these, it
Okay.
means the other one will not match.
Okay.
That means
So
all the table, there's so much.
there is no match. Very good. Because if you check this group and this group, there is no match. And if you check one of this with this also, there is no match. So it means that we have exhausted all our matching. So
They are tired.
so the loop will end. I told you if we were to do program, this will be in a loop, and then we continue to repeat it. So the loop only stops running when it identifies that there's no more matching to do. So this is our final table. So from this final table now, what we are going to do is that since if you look at the match pairs, they have the same mean terms. M0, M0, M1, M1, M8, M8, and M9, M9. So it's the same thing. So here, we are going to take only one of these mean terms. So it means technically the mean terms here are 0, 1, 8, and 9. Agreed? 0, 1, 8, and 9. These are the mean terms
Yes, sir.
that correspond to this. And the output is also dash 0, 0, dash. So what we are going to do is that we are going to do away with where the dashes are. It means that these variables will disappear. You see that in K-map, some variables were disappearing. So in the same way, here, the dashes are the variable that will disappear. So which ones are left? So here we
The
have
X and Z, the Y
we
and
have
Z.
Y and Z. So what is the mean term corresponding to Y and Z? What's the mean
M1
term
and
corresponding?
M
M1 and M8.
What's the mean
M
term for this? What's the mean term?
says 0.
One. It's one, so we have to invert it.
Very good. The mean terms that produce this are this one. But what is the mean term corresponding to this and this? You know how we write our mean terms from the truth table.
Yes,
What is
please.
the mean term?
It have to be one. So
Inverted Y and
we,
Z.
What's the mean
mean,
term?
mean
I
terms
don't
are
understand
the
that one.
ones are the
M1,
ones in the
M8.
table.
No.
The mean
Leave these
terms are
ones.
the
Leave these ones. These are
the
our variables, right? These are our variables. Remember how we form our mean terms from the truth table based on the variables and whether they contain 0 or 1, right? So anytime you are asked to write the mean terms in terms of the input variable, these are the input variables. So this is 0, this is 0. But these ones have gone. So we are left with only y and z. So you have y bar, z bar.
Z bar, okay.
Is that okay? That's the mean term corresponding to this input.
Okay, sir.
Yes, please.
And because this and this are the same, we just take this. So now we come here. The same way we have 1, 1, 3, 3, 9, 9, 11, 11. So we have only 0. Sorry, we have only 1, 3, 9, 11. So what's the mean term for this?
Sir,
Y
Y
bar
bar
W.
W.
Very good.
Y bar.
Y bar W, right? Because
W.
W is 1.
Yes.
So Y bar W. Then let's go to the last one. What's the mean term corresponding to the last one?
Say Z
S
W.
W.
Z
W.
and
ZW,
W.
very good. ZW. So we have it here. So what we have obtained from our final table here are the prime implicants. So these are the prime implicants. Remember we spoke about the prime implicants? So these are the prime implicants. Good. At the end of the day, okay, when you are forming your final minimized expression, it is usually made up of prime implicants and essential prime implicants. Your final expression is usually made up of prime implicants and essential prime implicants. But in most cases, we have only essential prime implicants. These are always part of your final expression. But in some cases, you may have some prime implicants also being part. So let's take note of this. Just as we did previously, when we're looking at the prime implicants and essential prime implicants, you realize that in your K-map, your essential prime implicants do not overlap do not have all its components being overlapped. So it is always part of your final expression. So based on the same principle, now we have obtained our prime implicants. But you know very well that from our previous discussions on the prime and then the essential prime implicants, some of the prime implicants are non-essential, and therefore we have to eliminate them. But now we have 3 prime implicants. We don't know if all these 3 prime implicants are essential or not, right? So we have to find out, are all of them essential? Then we keep all of them. If all of them are essential, then our final expression will be y bar, z bar, plus y bar w plus zw. Then this will be our final expression. But as it stands now, this table only produces prime implicants. So we have to go a step further to check whether all these are prime or some of them are redundant, which means we don't need them in the final expression. So that is the next step to do. So let's move on to that. So it says that make a prime implicant table. So we are going to make another table called the prime implicant table. That consists of the prime implicants as the obtained mean terms as rows and the given mean terms as what? Columns. So now we are going to make a prime implicant table. And the given mean terms, there are 2 sets of mean terms that will be in this table. The obtained mean terms and the given mean terms will be columns. So what are the obtained mean terms? Question, Patrick?
Yes, sir. I have a question.
Yes, go ahead.
So my question was, we dealt with step 1, 2, and 3, and now we skipped step 4, and we are dealing with step 5.
This is step 4. Okay, so let me read step 4 so you can get it. Did you see step 4? Because I already spoke about it. We repeat this 2 and 3. I think I mentioned this, that we repeat it again and again till we cannot further find a match, right? So that is the step 4.
Sure, you did.
Very good. So that represents our step 4. Are you okay?
Yes, sir.
Good. So it's a step 4 that got us to this point where we notice that there's no further, matching. So once we do the repetition many times, then after that, that's the step 4. We repeat. And then we end up with this table. So the output of the step 4 is this. That's why I wrote here step 4. So it means that after repeating, we end up with a table where we can't find matches again. And this becomes our final table. Okay, good. Now, if this is our final table, and I've already explained that we need to form the prime implicant table, which consists of the obtained mean terms as rows and the given mean terms as columns. So the obtained mean terms, you remember I was talking about mean terms. So we have 3 groups now. So the obtained mean terms are these: mean term 0, mean term 1, mean term 8, and 9. Then for this group, we have 1, 3, 9, 11. Then 3, 7, 11, 15. So these are the mean terms that we have obtained at the end of the whole process. But we are also given a mean term from the beginning. So the mean term that we're given from the beginning is what? M0, M1, M3, M7, M8, 9, or to 15. This is the given mean terms, right? And this is what we had. So step 5 says that we should write the obtained mean terms. So we have the obtained ones, which are 3 sets of mean terms, each corresponding to these mean terms that we have obtained, right? So the mean term corresponding to this guy is what? 0, 1, 8, 9. So we have 0, 1, 8, 9. Then the mean term corresponding to this is 1, 3, 9, 11. So we have 1, 3, 9, 11. And then the last one is 3, 7, 11, 15. So this is the obtained mean terms that correspond to our prime implicants, which is the PI. And the step further says that
Hello,
these
sir.
should be rows,
Take
right?
that part again. My network dropped.
These are our rows, the mean terms. So the obtained mean terms, these are the rows. So first row, second row, third row. Then it says that the given mean term should be the columns, the given mean terms. And we know the given mean terms is 0, 1, 0, 1, 3, 7. That's the original mean terms given to us. Good. So now what we are going to do is that we are going to see if all the mean terms that we have obtained, they align with all the given mean terms in the original function. So at the end of the day, we must make sure that all the mean terms that we have obtained, they match with all the mean terms given. So how do we do that? So we take the first row and try to see where it matches with the given mean terms. right? So this one contains 0, which matches with this. It contains 1, which matches with this. It contains 8, which matches with this. It contains 9, which matches with this. So it means that our first mean term here that we have obtained has already satisfied 4 of the given mean terms. We move on to the next and see which of the mean terms this guy also matches. This guy also matches 1. Again, let me use a different color. This one also matches this one, and 3. It takes 3. 9 takes 9 again. So that's what we have here. We put star. Then 11. It matches here. We put star. So it means that this one also matches the given at 1, 3, 9, and 11. Then we take the last one. Let me use is it the pink or whatever? So this one. So this one matches 3. So we have 3 here. This one matches 7. We have 7 here. This one matches 11. We have 11 there. And this one matches 15. We have 15 here. So you see that all our mean terms have actually covered all the mean terms given. But let's check. Do we have some redundancy or overlap? Because you realize that some of them are actually overlapping. So
Yes,
what
sir.
we are going to do is that to find out the mean terms that are essential, the prime implicants that are essential, we check the columns. We check the columns and see which of the columns have only one match with our given mean term. So if you look at this column, you see that there's only one match, right? This one has 2. This one has 2. This one also has only one match. So we are now considering columns that have only one match. This one also has only one match. And this one also has only one match. So these other columns that have 2 or more matches, we leave them for now. Now, take the columns that have the 1 matches. This guy, this guy, this guy, and this guy. Now, which of our prime implicants correspond to these ones, these matches? Which prime implicant correspond to this, and this? Which of the prime implicants? I mean here, which of these are prime implicant correspond to this and this?
X bar, Z bar, and ZW.
So is here, right? So this one, we can see produce only 1. So these ones correspond to this, Y bar, Z bar. Then you realize that this and this also correspond to what? W, Z, ZW. This one also corresponds to ZW. So it means that it is enough for us to use Y bar, Z bar, and ZW to cover all these mean terms, and we are good to go. So technically, this is not really needed. This is a non-essential prime implicants. Since this and this are those that produce only a single match in these columns. So this and this becomes our essential prime implicant. But there is one more thing to check. Since we are now selecting this and this as our essential prime implicants. In the beginning, you realize that when we use these mean terms, and these mean terms to match all this, we're able to match everything. At the end of the day, we must make sure that all these mean terms are able to cover all the given mean terms. But there were some overlap, and we didn't know what was causing the overlap. But now we have been able to unravel and see that there were some redundancy. And now only the Y bar, Z bar, and ZW is the essential. It means that this and this should be enough to cover the whole mean terms. So how do we ascertain this? So what we are going to do is that if indeed we are saying that the Y bar, Z bar, and then the ZW are our essential, it means that the mean terms for this and this should be able to cover all this without leaving anyone out. So let's see. So this one contains 0. So it covers this. 1. It covers this. 8. It covers this. 9. It covers this. We still have 4 that is not covered. Then we come to the other essential prime implicants. So 3. 3 is covering this. This one is 7. It's also covering this. This is 11. It's covering this. And 15. Wow. It's covering this. So you see that taking only these 2 is enough to cover the whole of this. So which means that this guy was actually not significant enough. Now, let's even try and assume that we don't know. We want to pick this one. So what is this guy coming to do? Because it has 1, which is already covered by this guy. It has 3, which is already covered by this guy. It has 9, which is already covered by this. It has 11, which is already covered by this. So it means that it's the same way if we draw the K map, all the cells of this will be covered by this and this. Just as we saw in our previous discussions with the implicants. So if you have all your mean terms being covered by other groups, then you become non-essential. Which simply means that this guy here would become a non-essential. And if we were to drop this and rather consider this as the prime implicants, what do we think would have happened? So what that meant is that we remove this, we remove this, we remove this. What that meant is that now, if we had dropped this guy and taken this, for instance, it means that we need this to cover the rest of the mean terms left. But can this guy cover the rest of the mean terms that are actually left? It can cover 1, which is already covered. It will cover 3. It will cover what? 9, which is already covered. It will cover 11 and 15. Right? This guy is left out. This one is never covered.
You didn't clean the 15.
Pardon?
You didn't clean the 15 when you were waiting for the first batch.
Yes. So I'm coming. So this one doesn't have 15, right? Good. So this one can best cover 1, 3, 9, and 11. And you see that 7 and 15, 7 and 15 remains uncovered, which means that this guy is not even enough. if we were to choose this and this as the essential prime implicants, that means that we will still have some of the mean terms here not captured. And that is a more reason why this is already disqualified. By taking this and this one was enough to cover all the mean terms, and therefore our final expression f will be given by the sum of these two. So y bar z bar plus z w, and that is it. Are we good? Yeah. So I'm seeing a hand up. Abuaje.
Yes, sir. Sir, please. It's, and please, can you take it get the details of that?
Your line is very terrible, so we can barely hear you.
Hello, sir. Can you hear me?
Yes, I can hear you now.
Yes. So I was saying now, all what you are doing had made me forget what you did. I would be
Pardon?
glad if you can take again the mean terms involved. How is it that the mean term involved for YZ?
I cannot hear you, please. So if you can reposition yourself, that will help.
Can you hear me, please?
Yeah, this is better.
Yes. So I was saying the mean terms involved. I'm a bit confused because I'm kind of forgetting what we learned earlier on. The whole thing is confusing me. So how did we get to the mean term for Y bar Z, which is 0, 1, 8, and 9? How did we get that?
Were you actually following the discussion? Because I have explained how we got to this point.
I've
You
been
were
here.
following the discussion, so you should know
Yes.
how we got to this point, because I've explained it. That is the mean terms obtained. This is the same as the mean terms obtained, right? Maybe the word involved, I don't know if it's the word involved that is confusing, but the mean terms obtained, I already explained here. I even told you that here we are looking at these mean terms. These are the mean terms that we have obtained. M0, M1, M8, M9. That correspond to this. M1, M3, M9, M11 correspond to this. M3, M7, M11, and 15 correspond to this. So these are the mean terms, the obtained mean terms, or the involved mean terms. The only thing we are doing here is we are not writing them with the M's. We are only writing the mean terms as 0, 1, 8, 9. But we could have just written M1, M8, M9, just as they are being written here, which I believe we all understand that you can write your mean terms this way, or you could as well write only the corresponding values like this. That is also acceptable. And here we have 1, 3, 9, and 11. And here you have 3, 7, 11, and 15, right? So these are coming from here, our own handiwork. Okay. So these are the obtained mean terms that we have in this row, which each correspond to our prime implicants, which is what we have obtained from here. So we are looking at where we have the dash disappears from that mean term. So it means that for this mean term, there's no X and W. We have been able to eliminate this. For here, we have been able to eliminate X and Z. That's why we have only Y bar and W. And here we have eliminated X and Y. And that is why we have only Z and W. So these are the mean terms that we represent these ones as the prime implicants. But we needed to know the essential prime implicants. And that is why we came here. So over here, we have gone through a number of processes, but the mean terms that you were asking about is the mean terms that we obtain in our final table here. Does that answer your question? That is, if I got your question right. Is your question answered? Who asked the question?
The Abuaji Prince.
Abuaji, and you have kept quiet. You will not tell us if your question is answered or not. Huh? Are you here?
Please, I think his network is
The
just
network is
worrying.
now.
It's muted. It's muted.
Okay, so I hope that that has been clarified. Any other question? Any other question? Any other question before we proceed? So this is our final expression. So I'll give you some problem to try. Yeah, later on. Do we still have some time? We can move on to the combinational and sequential circuits.
Yes, sir.
We have some few minutes.
We have about 17 minutes.
Okay, so let's continue with our combinational logic. I think this is also part of the Are we okay? Is everything fine?
Then my head aches.
Yes, sir. Yes, sir. Everything is fine here.
Should we run away? Who is that?
Because somebody is calling the name of Eradi, and I don't know what the problem is.
Vida.
You don't understand. Why are you calling
What's
God?
the problem?
Why are you calling
My
God
head
here?
is aching me, and it's
Ready for you,
again.
Sir, I have a question.
Our CPU is on too. Sir.
Yeah. Yes, go ahead.
Sir, the prime implicant table. Can you go back there?
Oh, you want to take us back to prime implicants table again?
I said that.
You don't want us to go to the combinational logic.
Yeah, my network was breaking, so I don't get
No. We have already sealed this, and I asked you a number of times. Okay, what do you want to ask? What do you want to ask?
The WY, I don't understand why the X are 4. I don't.
Which one?
Like how you
the
giving
network
this.
is really boring this morning from.
Please, can we have a common voice? If you have a lot of people talking, we won't be able to get your problem. So can we talk one after the other?
I don't understand how you constructed a prime implicant table. The X, where you put the X, I don't get it.
Okay. I think your question have been answered already. Yes, the next person. I have already answered that question. Next.
Okay, sir. Please, I wanted to find out how questions are based on how questions are set based on this.
I'm not getting your question.
I'm asking how questions are being set on the masculine.
What?
It's too early. It's too early. It's too early.
Please, who is the one asking the question?
Hello, sir.
Yes.
Hello.
Yes, go ahead.
Please, I just want to find out how person all the tables for all the various tests or what.
Please, this is the first thing we. Please, can you mute yourselves? If you are not contributing to the floor, mute yourself. This is the first question that we looked at before starting the whole table. I'm not sure if you actually saw this one earlier, because this is the question we're trying to solve. And that landed us in the whole tabular method thing and eventually got us to this final answer. Okay, so this is the question we are solving. In case you missed it, simplify the function below using tabular method, and this is the function.
Okay.
Rita, are you okay?
Yes, please, I'm okay.
Yes, so this is the question we are solving. And I have provided another question here. Using the QM method, simplify the function given by this. So it's always going to be simplification because the Quine-McCluskey technique is for simplification. Then you'll be given the function. The function you are supposed to simplify. Then you go through the process. Okay, please mute yourself because there's a lot of feedback coming from your end. So mute yourself. Next person, let's hear you.
Hello, sir.
Yes, go ahead.
Yes. So please, per what you are saying, does it mean that you always be giving the midterms, or there will be a logical function, and then you would have to find the midterms before you proceed, or always you will be giving the midterms?
Well, it depends on the question. But you always need to get the mean terms first. You always need the mean terms to be able to proceed. So there are different ways mean terms are presented. I hope you know that. It is not always in this form. We can give it to you in the form of an expression. It can be given to you in different forms, which we have already seen. This is just one form of presenting the mean terms, as you see. There are other forms of mean terms like this. You can be given an expression like this, and this is also a function. So when you are given a function like this, these are mean terms. So you can use these ones to derive the numbers, to derive this form. Okay? So just note that you will always be given the function. And this function can directly give you the numbers, or it will give you the expressions which you can use to derive the mean terms or the numbers, whichever way this should be possible. Is that okay?
So please, can you try driving the midterms from that?
No, we can do this. We have done this before. So if you can't do this, that means you need to go back check because we have already done this before. So I'll entreat you to revisit how to obtain mean terms. And this is something that we have done even, I think, in our last meeting. We have discussed this. So you may want to check on the slides again and revise if you may have forgotten. Okay. Because the task here is not to derive mean terms again. That is something we did last semester. And I hope everybody knows how to obtain mean terms per that discussion. Okay, so, but of course, it's in the slide. So in case you are missing that part, you can always go back and check. Any other question, please? You are trying to exhaust my remaining 17 minutes, which I will not agree. So let me proceed. So let's move on to the combinational logic. It's just going to be brief because we have discussed this previously. Okay. So in designing logical circuits, there are two main, classes of logical circuits. We have the combinational circuit and we have sequential. What's the difference between combinational and sequential? Can someone tell us? What's the difference between the combinational and sequential? Any idea? Otherwise, I will go and revoke your grades because those of you who have gotten the A's and the B's, I'll go and revoke it. If you cannot tell me the difference between combinational and sequential, I'll be very much surprised. So let's speak up because you should know this. We have done this before and we have gone past this.
The combination now, the output depends on only the input.
Okay. And sequential. And sequential.
All right, so the sequential depends on the current input and the past inputs.
Yeah,
Okay.
I think so.
Okay, that's a good one. Any other person?
And
Okay,
also,
so
the sequential has memory elements.
good. So in simply put, combinational and sequential logic, they are both type of logic design approaches, right? In digital logic design. So anytime we have a problem, we need to be able to tell if that problem requires a combinational logic to solve it or a sequential logic to solve it. Now, the difference is very simple. For combinational logic, okay, all the time, you have some inputs and some outputs. So you can have n number of input and m number of outputs, whichever. So for combinational circuit, all the time, your output here depends on your current input. So if your input is X and Y, it takes in values 0, 0, 0, 1, 1, 0, or 1, 1. Let's say your output is 01, 02, 03. So it means that whenever the value of your input changes, 0, 0, maybe the output here would give you 0, 0, 0. Sorry. But when your input changes to 0, 1, to 0, 1, maybe your output will change to 0, 1, 0. When it changes to 1, 0, your output changes to 0, 0, 1. When it changes to 1, 1, your output changes to 1, 1, 0, something like that. So you see that all the time, your current output depends on only your current input. This is combinational logic. So anytime there's a change in your input, there is a corresponding change in your output. But in sequential, what happens is that in sequential logic, if you have current input, let's say X and Y, and you have your current output, let's say A and B, anytime an output is generated, there is a copy of this output that is stored somewhere. So this output is stored. So when the value of X and Y changes, let's say X and Y were 0, 0 before. When it goes here, this guy is 0, this guy is also 0. So now we have 0, 0 stored here. The issue is that this guy always comes as a feedback. Yeah. So now if this input changes to 1, 1, if this input changes to 1, 1, you realize that it is not only this 1, 1 that is going to affect the output. The previous output for the 0, 0 also comes here. So you have 0 here, 0 here. So in other words, even though this has changed to 1, 1, but the 0, 0 from the previous output is also going to affect how the next output will be generated. So this is a sequential circuit. So you can see that at any point in time, the output depends on your current input and your past output, which is this. So this two determines your next output. Whereas with the combinational logic, your current input is all the time what affects the current output. But with sequential logic, your current output is always a function of your previous input and your current input. So you can say that your next output depends on your past output, which is this, and your current input. This is always current, but this is your past output, or the input of your past output, whichever way you call it. But we know that in sequential, it is not just the current input that affects your current output, but also the past outputs. Is this clear enough to everyone? Yes, so that is basically what the combinational logic is, different from sequential. So in our previous discussion, we spoke about a number of combinational logic. It has a lot of application. We have a lot of application of combinational logic and a lot of application in sequential logic in digital systems. So combinational logic, they are used in designing of adders, subtractors, comparators, for logical comparisons or logical functions. Now, if you take a look at our computer system, you realize that we have always been talking about the CPU, which happens to be one of the most essential components of the computer system. Now, CPU does a lot of computations. So if you open the CPU, what do we see? We see a lot of arithmetic and logical components. So we perform addition, we perform subtraction, we perform comparison operations, we perform multiplication and all of this. All these operations happen within the CPU. So these operations are handled separately by separate units. So for addition operation, we have the adder. So we have an adder which is already designed and is inside the CPU. we have the subtractor, which is also there. And these are all combinational logic. So the adder is a combinational circuit, which is designed to perform only addition. The subtractor is also a combinational logic, which performs only subtraction. You have the comparator, which performs logical comparisons. So these are all very useful components that we find within every digital system, including the computer system. So they are actually practical applications of these things. They are just not circuits, but they have been used to implement functions within digital systems like the computer systems. The sequential logic, because it has the capability of storage, because you see that anytime there is an output, that output needs to be stored. So it means we can use sequential logic to create storage where we can always store something that we need in future. And that is the basics of storage in computing or in digital systems. So we are going to see how we can leverage sequential logic to design storage elements. Today, we are all excited about storage. Everybody wants storage because, in our computer systems, in our smartphones, we all need bigger storage. But the question is, do we know how these storage elements are created? How are they designed? As computing students, this should be a concern. We are not just consumers. We should also be producers, because I know many of us are into some computing areas, and some of us are still aspiring to become professionals in the field. And, digital logic design is one of the key areas of computing, because if these things are not there, how do we get the devices? The computer systems that we are using, someone has to design all these components. So it is not just about software, the hardware is very important. And that is why in our previous course in Dcit 102, we went through a lot of design processes in hardware. So each of these components has to be designed using some logic, which we have seen. So for now, we will focus on combinational circuits, and later on, we will revert to look at sequential, how we can design sequential logic to store some bit of the information or data. Okay. Now, so as I said, combinational logic, this is a block diagram. So every combinational circuit takes in some input variables and it produces some outputs, right? But the number of input and the number of output depends on the problem that you are trying to solve, because different combinational logic would come with different inputs and different output, So we have classifications of this combinational logic. We have a class that is designed to perform only arithmetic and logical functions. So that is where we have the adders, the subtractors. They are combinational logic that perform arithmetic and logical operations within every digital systems. Then we have data transmission. Don't forget that in computing or in computer systems or computational systems, when I talk about computational systems, I'm just talking about any system that performs computation. It is not only computers that perform computation. We also have other components, other devices that perform computation. So computational systems do not only compute, they also transmit. If you take a critical look at the operations of the computer system, the CPU and the RAM, we have seen this before. We've seen how active these two guys interact. There is always some transmission of signals or data to and fro amongst these guys. So the CPU is always getting some data from the RAM, or your memory is always getting some data or information that has been processed from the CPU to store. So there's transmission going on. How are these transmissions designed? How are the channels that does this transmission? How are they designed? So it means that whilst the arithmetic and logical function, they are computational units, we also have transmission unit that handles how we move signals throughout the system. And there we also have a number of combinational logic that we can use to transmit information or data to the multiplexers, the demultiplexer, the encoders and decoders. These are what we will be looking at. Then the last class is code converters. How we can convert from one coding, like maybe a binary to BCD, so we can also do that. A typical example of the code converters is the binary to BCD 7-segment display, which we are going to see now. In our digital world, we always come across LEDs, which are displaying some lights, and once these lights are displayed, we see either some text or some numbers being written. If you take your digital watch, you see how the numbers are displayed. This is a LED, and these are actually formed from code conversion. So you convert from a binary number to a BCD. So later on, we'll look at how this is done. So we can use a combinational logic to also accomplish this. So in all, combinational logic is very, very useful in design. Without combinational logic, then most of our digital system that we see will not be able to do anything, because once you can compute, you can't transmit, you can't convert, then what can you do as a digital system? If your computer system cannot perform any arithmetic function, if your computer system cannot perform any transmission function, and your computer system cannot perform any conversion from one type of data to the other, then it is as good as an empty box. It cannot do anything. So this tells us that combinational logic is very, very important. And that is why we need to go into this and try to understand how these things are done. So when you are interacting with your computer system and your CPU is doing all this magic, you know exactly what is going on. You know how the CPU is doing the addition. You know how CPU does subtraction, how it does comparison. And we also have the PLDs, which is the programmable logic devices, which we are also going to see. So this is a summary of what we would be looking at. So far, we have seen the adders, we've seen the subtractors and comparators, right? We treated all this, isn't it? Yes, so with the exception of the PLDs for the arithmetic and logical function. So in our next meeting, we'll be looking at, I'll just give a little snapshot on the other subtractors and comparators, and then we move on to look at the PLDs. But before that, I'm going to share the lecture resources with you on Sakai. So try and download them. So the QM, I think I've already shared the QM, right? Do you have it? Yes. The Quine
Yes, sir.
McCluskey, the Quine McCluskey,
Yes,
I've already
we
shared
do
that
have it.
slide. Very good. So the next is the combinational and the combinational logic. I'll share that one also. So you can do a revision, go through it. And for those of you who may not also have the chance to take this, you can also go through it. And in our next meeting, if you have any question, you can ask. Is that okay?
Yes, sir. Thank you
Yes,
so
sir.
much.
Thank
All
you very
right. So
much.
guys, thank you all for staying by and enjoy the rest of your Vals Day.
Vals Day too. Happy Vals Day to sir.
Yeah.
Bye-bye, sir.
Bye.
Yeah, we're celebrating that one.